Let's get started. Here's the agenda. I'm going to cover the most recent updates in Ansys Fluent on user interface, meshing, turbomachinery, battery modeling, multiphase, moving mesh, turbulence and acoustic, high-speed compressible flows, combustion, heat transfer, Fluent structural model, solver numerics, and at the end we will have a Q&A sections. And I would like to emphasize that today's presentation does not cover the entire Fluent updates, but I'll go through the selected important ones today. If you're interested, you may visit Ansys customer portal for the full updates and enhancement. Let's start with user interface and graphics. In addition to the default theme, Fluent now has the new dark theme, and you can choose this in Fluent user appearance. And you can now include plots or visualization scenes in embedded sub-windows. Simply right-click and select Move to either reverse windows or any predefined scenes. Fluent Simulation Reports is a new capability in 2021 R1. The simulation reports make it possible for you to summarize and share the setup and results of your simulations. Key aspects of your simulations are compiled from your project settings and can be exported in either HTML or PDF formats. And also reports can be customized to suit your specific needs. When you have a complete Ansys Fluent simulation with saved case and data files, you can open the report outline using the simulations task page from the outline view, as you can see on the right here. Let's talk about Fluent meshing now. For those who are not familiar with Fluent meshing, it's a powerful and recommended tool for generating CFD mesh that has some unique features. Number one, it is integrated with Fluent, so you will work on single window from meshing to solver mode. That makes the workflow easier. Number two, it has mosaic meshing technology that uses polyhedra mesh in addition to conventional TET and hex mesh to make a better transition from different mesh types. Number three, it's very intuitive and you can observe everything right away. And number four, the new task-based workflow make the streamlined very user-friendly by elimination of several manual steps. So you can quickly generate high-quality mesh without the need to be being expert. Fluent meshing has two general workflows, as you can see on the right. The watertight geometry workflow for clean and defeatured geometry. However, sometimes you have a very complex geometry that requires a lot of time and substantial effort to be defeatured and clean up. For that scenario, Fluent meshing offers additional workflow that's called fault-tolerant meshing workflow, which uses wrapping technology to quickly generate the high-quality mesh for dirty geometry. The new capability in 2021 R1, volumetric mesh transformation. After you have created volume mesh, you can add the transformed volume mesh task to your workflow. This task allows you to create and apply translational or rotational transformations to your volumetric mesh, as you can see in the picture here. You can also add the extrude volume mesh task to your workflow. This task allows you to extend out the volume mesh beyond the original domain. For example, as you can see on the right, you can extrude your outlet to damp pressure reflection from static pressure boundary condition. In watertight workflow, you can now create local refinement regions. When simulating flow within and around an object, your geometry may not contain a fully defined refinement regions or body of influence. If a volume region needs a mesh refinement, that region can be identified by a watertight surface. And you can manually create such a surface in the Create Local Refinement Regions task. by defining a bounding box around one or more selected objects or creating an offset surface. For example, this volume region on the right, which surrounds the relevant aspects of your flow physics, can be used to as an alternative to refine the mesh in a particular area, such as in the wake region behind the vehicle, as you can see here. In fault-tolerant workflow, now you can create overset meshes, which is a new capability. So the task-based workflow allows you to create component and color mesh, as you can see here. The workflow also allows you to intersect and identify orphan cells before moving into the solver mode. The presence of orphan cells generally indicates that there is insufficient overlap between meshes or that the mesh resolutions do not match well. Let's review the turbo machinery updates. There is a new default method for mixing plane for handling of non-overlapping interfaces such as lip features, and this method allows us to change lip step features into injection or bleeds. To model this feature, if exists in the geometry, you must select the non-overlapping wall option when creating a general turbo interface. The non-overlapping part of the interface forms walls by default, and these walls are listed with wall boundary conditions. If the lip feature happens to represent a region of injection or bleed, then you can change the boundary to an inflow or outflow boundary. And aerodynamic damping is enhanced in 2021 R1. The forced vibration analysis in turbo machinery is essential for predictions of blade structural failures. An important ingredient in this analysis is the prediction of the blade aerodynamic damping value from blade flutter analysis. And the damping value directly impacts the characteristics of the vibration of the blade response. So there are a couple of enhancements here for traveling wave mode, energy method, real or complex shapes, monitoring, and contour generation as well. Battery modeling updates. The battery model is now available directly in the graphic user interface, and you can select this module in the outline view or from the physics tab under models section of the ribbon. Previously, the battery model could only be activated using the TUI command as add-on module. In conjugate heat transfer, energy source terms and tap current can now use transient profiles in battery modeling. And when there are many active zones, you have the options use same settings for all zones. That eases the setup process instead of manually go through the individual zones. And now let's talk about the updates in multi-phase flow simulations. For VOF-free surface flows, there are a couple of enhancements in 2021 R1. The first one is a solver enhancement for explicit VOF, which is especially important for high-speed moving mesh applications. The second one, adaptive time stepping, is improved by considering of several additional time scales. Number 3, there is an integrated GUI for VOF stabilization methods and hybrid NETA. And number 4, improved default settings for VOF mesh adaptation criteria. And number 5, automatic turbulence initialization that overcomes unphysical initializations of turbulence. VOF with geo-reconstruct interface scheme in 2021 can be run up to 10 times larger time steps than 2020 R2 without losing stability. Look at this results comparison here. Let me play the animations. In 2020 R2, unphysical results start to show up with current number greater than 0.1. But on the right, in 2021 R1, running with a current number of 1 still shows good results. A very cool feature that was previously introduced in Fluent version 19 was model transition between volume of fluid and discrete phase model, VOF and DPM. In a liquid space simulation, distinct droplets are detected and replaced by mass point particles, and mesh is coarsened accordingly. And this significantly reduces the total mesh number and speeds up the computation. In 2021 R1, Ansys Fluent added DPM to VPM transition as well. So particle falling back onto a free liquid surface transitions back into VOF formulations, meaning that mass point particles replaced by mesh resolved liquid. In addition to VOF and DPM transition, there is additional transition to Eulerian wall film. So you can simultaneously have all these three flow regimes in your simulations. The three small Lagrange parcels have fallen onto a surface forming a Lagrangian film, and depending on the film height, the film is replaced by VOF. And similarly, thin layers of VOF liquid adjacent to a wall can be replaced by Lagrangian wall film. Here I'm showing you an example of these flow regime transitions, and let's consider windshield wiper example. The first one on the left just shows the rain particles. The middle one shows the liquid film thickness, and the one on the right shows the volume fraction of liquid. Another example, DPM droplets impinge on the wall, forming a film using Eulerian wall film, and Eulerian wall film separates into DPM droplets, and droplets fall onto floor, again forming a film, and Eulerian wall film transitions to VOF as well. So all those three transitions in one single simulation. Moving mesh and overset. In 2021 R1, Puma-based dynamic mesh adaptation technique extended for overset problems now, which enables the combination of overset-specific adaptation with solution-based adaptation criteria. So this capability is a new features in 2021 R1. A new remeshing framework has been added in moving mesh applications. It's called unified remeshing, which eliminates confusing selection among different remeshing methods, like local cell, local phase, region phase. So you have one single option, unified remeshing, that can consider all those together for you. Turbulence and acoustics. An interesting recent acoustic feature, you can now listen to your Ansys Fluent simulation. You can generate sound files and psychoacoustic indicator values from within Fluent 2021 R1 and use VR experience sound and Ansys virtual reality tool for sophisticated sound analysis. Additional options in turbulence modeling that account for corner flow correction, and this helps account for turbulent flows through rectangular channels or pipes of non-circular cross-section and wing body junction type geometries that exhibit secondary flows in the plane normal to the main flow direction into the corner along the bisector. High-speed compressible flows. In 2021 R1, there is an additional energy modes 2-temperature model. When using the density-based solver, a 2-temperature model is available for simulating the thermal non-equilibrium phenomena in hypersonic flows, and it models the energy relaxation process in the flow and provides a better prediction of the flow fields than the 1-temperature model. NASA 9 thermodynamic data has been added, which is important for accurate properties in hypersonic or high temperature aerospace applications. This new data is available for both pressure-based and density-based solvers and for all species transport models. Combustion. For effusion orifices modeling, large number of small orifices make it impractical to resolve all the details in the mesh discretization. The new perforated wall boundary condition allows you to model the effusion holes without resolving them in the mesh and reduces the simulation time accordingly. Here you can see the comparison of the computed temperature and mixture fraction for resolve and model diffusion cooling holes. Small percentage difference implies that you can use the perforated wall model without losing much of accuracy, but still have a lot in, you can save a lot in computational time. Let's talk about the updates in heat transfer. There are two new approaches for accelerating transient conjugate heat transfer simulations. The first one is time average explicit coupling, and the second one is loosely coupled multi-domain method. In the first one, in the explicit coupling, fluid and solid solutions are advanced at the same time intervals, and it's suitable for cases where fluid physics requires small time steps, but rapid evolution to a quasi-state solid solutions is required. On the other hand, is loosely coupled approach, fluid and solid are advanced at different time intervals because fluid and solid regions are solved separately. And it's suitable for cases where fluid physics requires small time steps, but fluid and solid transient solutions need to be kept at same physical time. Here shows you the performance of using a loosely coupled method in a conjugate heat transfer solution. 15% overall speed up and 70% speed up in energy computation. So speed up is proportional to the solid to fluid cell count, and in this example, the ratio was 0.7. Mesh interface enhancement, one-to-one creation method is now default, and Fluent will automatically detect and create one-to-one interface pairs for any selection of wall interface zones. List button now lists by parent interface boundary instead of listing by interface names. And legacy many-to-many interface creation is only available via TUI now. As I mentioned, we have a better visualization list grouping of mesh interfaces now. Fluent will display the intersected zones generated during mesh interface creation, which is helpful for diagnostics and evaluating quality of interface. You can choose interface by name, material type, zone type, or even adjacency. Two case studies shown here for electric motor case, more than almost 10 times speed up, and for grinder case, about 7 times faster solutions were obtained in 2021 R1 as compared to 2020 R2. So performance is case dependent, and number of mesh interfaces has a larger impact on the performance than raw mesh size. Fluent structural model has some updates. Let me play the animation. The structural model in Fluent now allows you to model linear or nonlinear thermoelasticity in order to simulate the effects of thermal load on solid structure deformation. And to set up such a solution, choose the thermal effects, the new option in the structural model dialog box in Fluent. Solver numerics. In 2021 R1, there are 2 new marking criteria to improve detection of poor quality cells. that are controlled by TUI command, as you can see on the bottom here. The two methods are combined residual and mesh quality criterion and quality of computed gradient. In adjoint solver, the Fluent optimization module now support non-constant material properties. For some applications like high-speed compressible flows, material property dependencies are very important during optimization. For example, this figure here shows more than 30% reduction in drag force by considering the non-constant material properties. For compiling UDF, there is no longer need to install a third-party Visual Studio compiler because Fluent 2021 R1 has its own built-in compiler to make this workflow much more convenient. So you don't need to install any third-party softwares to compile your UDF now, and this is the first time that Fluent has its own built-in compiler. The last slide shows the substantial performance improvement in reading and writing files in Fluent. As you can see in the table, for a test case consists of 10K zones. There is 2 times speed up for common fluids format, case reading, and almost 3 times speed up in case writing. Also for legacy format, you can see there are significant speed up in both reading and writing case files. This is the last slide on Fluent 2021 updates. Again, for full updates, you may visit Ansys customer portal. And here I've tried to cover the most important updates that are relevant to our customers' applications. And before going to Q&A session, let me quickly go over the next few announcement slides. Here, I would like to let you all know that we can provide with you with free trials of Granton material selectors, Ansys Cloud, and Ansys Learning Hub. So if you need a free trial of any of these, feel free to reach out to us and we will be happy to provide you with this. And just want to remind you about the free registration for Simulation World. Ansys will host this virtual event for 3 days in a row starting from April 20th. So the registration is now open, and save your spot by signing up today. You can sign up for Simulation World through our website, aopds.com, using the direct link on the home page on the top. And last but not least, there will be more webinars on various topics, as you can see in these tables. And you can check this out again in our website, aopds.com. And make sure to visit our website, LinkedIn, and our YouTube channel. Thank you very much for your attention.